Good morning, class. We're starting right away, and I will wait for anybody. Class starts by 8 a.m. and this is 8:03. So we are starting right away. Continuing with our molecular bonding, and we are moving on to intermolecular forces. And I want to lay a foundation of this. As we know that the previous types of bonding we have looked at, the ionic or electrovalent bonding and the covalent bonding, whether dative or ordinary covalent, are the bonds that occur between atoms in molecules. So we can term those ones as intramolecular forces. These are forces of attraction that hold atoms together within a molecule. And we are progressing further now to what we call intermolecular forces. And these intermolecular forces are forces of attraction that hold molecules together. So intermolecular forces are forces of attraction or bonding that holds molecules together, different molecules. So within a molecule, you have intramolecular force, and between molecules, you have intermolecular forces. And we have two major types. We have the van der Waals forces, and the hydrogen bonds. And these intermolecular forces are not as strong as the intramolecular forces. So these are kind of weak forces that exist between molecules between molecules. And under the van der Waals forces, we have the dipole interactions and dispersion forces. And we also have hydrogen bonds. In the course of the lectures, we'll explain each of these forces. So now we have a few queries to look into. We have some solids like sodium chloride, your common salt. It dissolves in water, is a solid. But whereas some other solids like your camphor, your naphthalene balls, they do not dissolve. So the fact that a molecule or a compound is a solid, some have the characteristic of easily being soluble in water, while some, no matter the volume of water you add, they will not be soluble. Another thing is that some substances at room temperature, they are gaseous, while some others are liquid or solid. So that means the state of matter, even though they have the same state of matter, they are not, even though they have the same state of matter, their solubility differs. And sometimes, even at the same temperature, you have some molecules that will always, maybe let's say at room temperature, they are gaseous, and some other compounds at room temperature, they are liquid or solid. Another question or query we have to think about is, why do metals conduct electricity? That means that electrons can move within metals, and some metals, non-metals, they are brittle, they are easily broken. Why do this occur? All these queries that we have looked at can be solved by looking at intermolecular forces. So why some solids will be liquid and some solids will be able to dissolve in water and some others are insoluble is as a result of these intermolecular forces. Why some substances will be liquid at room temperature and some will be gaseous. Even so, why will some easily get sublimed they just move from solid to gaseous state, even at room temperature, without adding any form of external heat? All these have to do with intermolecular forces. So now, like I said before, in molecules, we have two types of forces of attraction: the intramolecular bonds, which we have looked at, your covalent, ionic, and electrovalent bonds, and the intermolecular forces. We've already looked at the intramolecular forces or bonds for ionic compounds and molecular compounds like your covalent and your dative or coordinate covalent bond, which we have described as attraction or forces of attraction between atoms in a molecule. But intermolecular forces have to do with the attraction between molecules. So when molecules are assembled together, there is a link between them. And it is this link that will determine whether a particular molecule will be liquid at room temperature, or whether it will be solid at room temperature, or whether it will be soluble in water or insoluble in water. So the intermolecular forces could be, we have what we call the partial ionic, we have dipole-dipole forces, hydrogen bonding, London dispersion forces, covalent, that is for network of solids, and we have metallic bonds. So all these are what we'll be looking at under intermolecular forces of attraction. So we're starting with the van der Waals forces. The van der Waals forces are actually the weakest form of attraction between molecules. And the force of attraction derived its name from the person who discovered it. That is J.D. van der Waals. That is his name. So, and this, if you look at this now, we have molecules. So these are different molecules. You can see the molecules. And these molecules have, there is the charged, you have the negative charge and the positive charges. And you can see now that there is an alignment because opposites always attract. So you have one molecule, and the molecule, there's a second molecule will induce the charge separation. So the charges are separated, and there will be a kind of an attraction between the negative end and the positive end of two molecules. So this van der Waals attraction is, opposites would always attract. Opposite charges have the tendency of getting attracted to one another. So when you have them aligned by close to each other, there'll be a dipole. The dipole means that there'll be an alignment of the charges, the negative and the positive charges. And when the molecules now come together, you will see a charge. There'll be a kind of attraction between the two the two opposite ends in two molecules. So this charge of attraction, or this force of attraction, is the van der Waals force. So when you look at a polar molecule, for example, it has two poles. Let's look at water. Water has two hydrogen atoms and one oxygen atom. And in water, as you can see, the charge, there is an alignment. The hydrogen atoms are positively charged, while the oxygen is negatively charged. So you have, at this end where you have your hydrogen, the positive end, and your oxygen, you have the negative end. So we can see that a polar molecule would have two poles, negative and positive charge. But there are some times when you have maybe like chlorine molecule, for example, there is not a polar molecule because the two chlorine atoms in the molecule are both negatively charged. So there's no polarity because the two charges, the two chlorine atoms in chlorine molecule carry the same charge. But a polar molecule would have two poles, a negative end and a positive end. And dipole-dipole interactions are the attractive forces that exist between permanent dipoles of two polar molecules. So when you have a polar molecule whereby you have a positive end and a negative end, there'll be a kind of attraction between the dipoles. So the electrostatic interaction between the oppositely charged regions of the polar molecules. So let's look at the example we have here, like acetone here. You have a carbon linked to the oxygen with a double bond, and you have carbon linked to the alkyl group. So this is the carbon linked to two carbon atoms and oxygen, and each of these carbon atoms are linked to three hydrogen atoms. And as you can see, the oxygen here is negatively charged. So it has a partial negative charge, while the carbon at the central molecule is positively charged. So there will be a kind of attraction between this pole, the negative end of oxygen, and the positive end of carbon. Similarly, the negative end of oxygen and positive end of carbon. So there will be a net of attraction of the permanent dipoles. In acetone, for example, the dipoles in adjacent molecules align so that the partial positive and partial negative charges are in close proximity. So they are aligned or arranged in such a way that there will be a kind of a pull or attraction between the opposite ends of the atoms in the molecule. So these attractive forces caused by the permanent dipoles are much stronger than the weak van der Waals forces. So this is a kind of a permanent dipole that occur the electrostatic interaction, which are in polar molecules. So there will be a permanent, the permanent dipoles are stronger than the weak van der Waals forces. Then we have what we have the ionic attractions. So in molecules that whereby you can have separation of charges, like your HCl, you have hydrogen is positively charged and chlorine is negatively charged. So this molecule, for example, has is a polar molecule whereby you have a positive end and a negative end. And apart from polar molecular molecules, this could also occur in ionic compounds. And note that the greater the electronegativity, the electronegative value, the greater the electronegativity, the greater the dipole. So those that are strongly electronegative would have a very strong dipole interaction. So the molecules here would be attracted to each other. So as we have two molecules of hydrogen chloride, they will be attracted to each other in a compound by the positive and the negative forces. So let's look at this example here. You see, you have a negative and a positive dipole in this polar molecule. This is the negative end and this is the positive end. When you have another molecule, a similar molecule of such, there'll be an attraction between this positive end of molecule B and the negative end of molecule A. And similarly, you can see this, the negative end of molecule A can also be attracted to the positive end of molecule C. And similarly, this can happen. So there'll be a network of all these attractions in the molecules that are aligned to one another. So this is another form of a weak intermolecular force that occur whereby molecules are attracted to each other by the negative and the positive forces. And this occurs in both ionic and polar bonds. So the London forces, now we've said that polar molecules, where you have your negative and your positive ends, can have an interaction, the opposite ends will attract. What occurs in non-polar molecules? In non-polar molecules, like I said before, the two ends have the same charge, like your chlorine molecule, whereby you have your each chlorine atom being partially negatively charged. So the non-polar compounds, how can they form? And you know, the linking of this compound, the molecules, can affect whether they will be solid, liquid, or gaseous, depending on the force of attraction between them. So the London forces are named after a man called Fritz London, which is also called the Van der Waals forces. So these London forces are due to small dipoles that exist in non-polar molecules. Non-polar molecules, even though they are negatively charged, the both ends may be identical, but there are some electrons that move around the atoms, and there will be an instance whereby the charges around the atoms are not perfectly symmetrical. You know that you have electrons, you have your protons and electrons, but the electrons that are moved, whether they're negatively charged and positively charged, between the two atoms that form that molecule, there'll be a time there'll be a greater density of electrons on one of the atom than the other. And when there is a greater density or electron cloud on one atom, there'll be a tiny dipole that'll be caused between the atom and the molecule. So I'll give an example. This is a diatomic molecule, as you can see, and these are the charges that, let's say, the two atoms are negatively charged. The same example I've given before, chlorine molecule. So this is a chlorine atom, this is another chlorine atom, and the two of them are negatively charged. So each of them have their charges as it were on them. So what happens next is, if you can't hear me, then you log in and you log out and log in again. I'm sure other people are hearing me. So at some point, when these individual molecules are placed to one another, at a time when this molecule come in contact with another one, a similar molecule, you see that these charges, you can see, let me show you, as the slide is moving. could see that the charges initially are equal, but they keep on moving. At some point in time, you see the alignment of the negative charges of the electron until a time comes that one of them would have a greater electron density around it. And the one that has the greater electron density at some point will be more electronegative than the other one. Eventually, the electrons are situated so that there'll be a tiny dipole formed between them. So when the two molecules come in, close to one another, there'll be an induced dipole on them. So I wish I could play the video. So the dipole forms in one atom and it will induce the dipole in the another molecule. So one molecule will form a dipole, instantaneous dipole, and when they are placed beside one another, the other one will be induced also to form a dipole, even though it is a non-polar molecule. Then we have the hydrogen bonding. It's a special type of a permanent dipole-dipole attraction that is very strong. One thing we need to know about hydrogen bond is that it is an intermolecular force of attraction, but it is a strong intermolecular force of attraction. And hydrogen bonding is that attraction between a hydrogen atom of a molecule with an unshared pair of electrons in another molecule. Remember, we're talking about two molecules now. Molecule A has an hydrogen atom, which has an affinity to another molecule that has an unshared pair of electrons on it. So hydrogen bonding from the name would always occur in molecules where hydrogen is covalently bonded to a highly electronegative atom, which also has a lone pair of electrons on it. So we are talking of two molecules. Molecule A has an hydrogen atom, and that hydrogen atom is now having an affinity to an electronegative element which has a lone pair of electrons on it in the neighboring molecule. So an hydrogen bonding would always occur in molecules that contain nitrogen, oxygen, and fluorine. And looking at these three atoms, on the periodic table, they are the most electronegative elements on the periodic table. Because if you look at the periodic table, electronegativity increases as you go from left to right on the periodic. And excuse me, can you all hear me? Because this person is saying he can't hear anything. I hope every other person can hear me. Please, I want to see your response. Can you hear me? Type in the chat box if you are hearing me. So if you are not hearing, it has to do with your connection, maybe where you are. So I would advise you to log in, log out and log in again. Thank you for your response. Thank you very much. So if you know you can't hear me, you log out and log in again, or change the location where you are. Might be your internet connectivity. So back to hydrogen bonding. So when hydrogen is has an affinity for another atom in a neighboring molecule, and that molecule is highly electronegative and has lone pair of electrons. And like we said on the periodic table, these three atoms are the most electronegative atoms on the periodic table, and that is nitrogen in group 5, oxygen in group 6, and fluorine in group 7. So if a molecule contains any of these, and these atoms have lone pair of electrons, so there is hydrogen in the neighboring atom, a molecule, there will be a nitrogen bonding between them. The high electronegative of nitrogen to hydrogen, or hydrogen and oxygen, or hydrogen and fluorine bonds can cause these strong forces to be to be 5 times stronger than the normal dipole-dipole force. So because of the high electronegativity of nitrogen, oxygen, and fluorine, these bonds, even though they are intermolecular forces, they are usually stronger than the normal dipole-dipole bond. So this is an example of hydrogen bonding in water. Remember we said when there is nitrogen, oxygen, and fluorine. So let's look at the one that has water. that has oxygen. So this is one molecule of water. See your oxygen in red and the two atoms of hydrogen. And from definition, hydrogen bonding will occur when these hydrogen atoms have affinity to an electronegative atom on a neighboring molecule. So see the water molecules are arranged around each other. So this hydrogen atom here, which is positively charged, will form, there'll be a dipole, and this oxygen in water is partially negatively charged. So there's an attraction between them. Remember, opposites attract. So in this case, this hydrogen would have an intermolecular force of attraction, attracting it to this oxygen. And on this oxygen in water, how many lone pairs of electrons are on this oxygen in water? How many lone pairs of electrons are on the oxygen in water? How many lone pairs of electrons are on this oxygen? I want to see your response. Your response. So yes, on water, remember our the Lewis structure that we drew. You will note that from drawing the Lewis structure, that there will be two lone pairs of electron on water. And as you can see here, you have your oxygen. When we draw the Lewis structure of that, you have your water. So this is your water. And from the drawing of Lewis structures, you have two lone pairs of electrons on water. So there are two lone pairs of electrons on water. So if you have another water molecule, so let's say we have hydrogen, so this is another water molecule, hydrogen, oxygen, hydrogen here. So this also, this has two lone pair. So this is, remember that this is partially positive, negative, sorry, and this is positively charged. So there'll be an attraction, and this oxygen has a lone pair of electrons. So there'll be an attraction between this hydrogen of molecule 2 and the oxygen in water molecule 1. Similarly, there's another water here. So this is what is also written here. So you have your oxygen here. This is negatively charged. Your hydrogen here is positively charged. And on this, your oxygen, there are lone pairs of electrons on this oxygen. So the hydrogen here, this is your hydrogen in this water molecule, will have an affinity for this oxygen. The hydrogen here also will have affinity. So if there's another water molecule here, for example, you have another water molecule that this is H. This is water. There'll be a bond, a nitrogen bond formed between this hydrogen and the oxygen that is here. So there'll be hydrogen bonds. So that's now, we have a giant network of hydrogen bonds in the structure of water. So looking at electronegativity, we know that an atom or ion's electronegativity is its ability to pull electrons towards itself in a covalent bond. So the most electronegative elements are found towards the right corner of the periodic table. And if you look at, recall, we said that carbon, oxygen, nitrogen, oxygen, and fluorine are the ones that can form hydrogen bond. Remember, on the periodic table, electronegativity increases as you go from left to right and decreases from top to bottom. So if electronegativity increases as we move from group 1 to group 8, and it reduces as you go from period 1 downwards, it shows that the most electronegative elements on the periodic table will be nitrogen, oxygen, and fluorine. And so we know electronegativity is the ability of an atom to pull electrons towards itself. So this nitrogen, oxygen, and fluorine will have that ability to pull electrons, and they have an attraction for the hydrogen in the neighboring molecule. So we looked at the example of water. We can also look at other examples of molecules that can exhibit hydrogen bonding. So you see the reason why now nitrogen, oxygen, and fluorine in groups 5, 6, and 7 will be the most electronegative elements, and they are the ones that will form hydrogen bond with hydrogen. So of all the intermolecular forces, hydrogen bonds are the strongest of all. And hydrogen bonds are possible. Hydrogen bonds are possible because in hydrogen atoms, there's no shielding of the nucleus. So because you have just one electron, and so there's no shielding of the nucleus with just that one electron, which is the first shell in hydrogen. So hydrogen bonds are responsible for the physical properties of many biological substances, and especially water. Molecules with hydrogen bonds have higher boiling points than molecules that don't. If you look at water, for example, water boils at 100 degrees centigrade. That's the boiling point of water, which is quite high. But if you look at the properties of covalent bond that we looked at, when we look at covalent bond, we said that molecules that have covalent bonds have low boiling points. And we look at water. Water has covalent bonds, but it does not have low boiling points. Water has high boiling points. The high boiling point of water is as a result of the high boiling point of water. The high boiling point of water So the high boiling point of water is as a result of the hydrogen bond that is that occurs in water. So, and you can imagine if water were to be boiling at 20 degrees or 25, or let's say 30 degrees, like some polar compound, like some covalent molecules, what do you think would happen in cases of, now, in the tropical parts of the world, whereby we could have an average temperature of maybe 35, in some places 40 degrees. That is the average maybe daily temperature. And if water were to boil at 35 degrees and the daily temperature of the atmosphere is 40 degrees, that means life would not be sustained. So nature made it such a way that the boiling point of water is high, so that even days where we have very high temperature, you won't see water boiling. If not, every one of us would have boiled off if the boiling point of water were to be very low. And what is responsible for this, like I said before, is the hydrogen bond that occur in water. So rather than water having very low boiling point, like normal covalent compounds, it will have a high boiling point because in addition to the covalent bond, the water is also having hydrogen bond with neighboring water molecules. So you can see another illustration of hydrogen bond. So let's look at this compound, methane. This is carbon, and you're surrounded by 4 hydrogen atoms. Would you expect hydrogen bond to occur in methane? I want your response in the chat box. Would you expect hydrogen bond to occur in methane? You can type your answer in the chat box. No. Somebody said yes. No. Even though methane, as you can see, methane has carbon surrounded by 4 hydrogen atoms. So if I have carbon surrounded by 4 hydrogen atoms, as you have your methane. So this is another methane molecule. So this is CH4. So this is your methane. So this is another methane carbon surrounded by 4 hydrogen atoms. So this is another methane. So the rule says that it's not just when you have hydrogen atom in the molecule, the hydrogen bond will occur. There must be the neighboring molecule. The hydrogen bond will only be formed between hydrogen and an electronegative atom in the neighboring molecule. And this electronegative atom must have lone pair of electrons. And in methane, is there an electronegative atom there? No, because there is no oxygen, nitrogen, or fluorine here. It's just carbon and hydrogen. So in this case, we don't expect hydrogen bonding to occur in methane because there is no electronegative elements which you have highlighted before, oxygen, nitrogen, and fluorine present in the neighboring molecule. So if this does not happen, we are not expected to see hydrogen bond in methane. So this does not have any hydrogen bonds. Carbon is not very electronegative like your oxygen, nitrogen, and fluorine. So therefore, the lone pairs of electron and does not have any lone pair of electrons. So we will not expect that to occur in methane. So if you're asked if methane would have hydrogen bond, you can see here now that there will be no hydrogen bond in methane. So let's look at another compound. This is ammonia. And you know in ammonia we have, let me try to annotate this. In ammonia, we have your nitrogen carrying the lone pairs of electron, as you can see, the lone pairs of electron here. And you have 3 hydrogen atoms surrounding ammonia. So in this case now, in ammonia, will you expect to find hydrogen bond in ammonia? Would you expect to see this? I want a response. So this is another molecule of ammonia. And you have a lone pair on this. So looking at this now, would you expect, yes, there'll be hydrogen bond. And why? Because we have hydrogen. The first criteria is hydrogen is present. And the next other criteria is that there is a lone pair of electron on the, so this nitrogen is our electronegative atom, and it has lone pair of electron on it. So this lone pair of electron will attract this hydrogen bond, would have an affinity for this nitrogen. So there will be hydrogen bond here. So if you have another molecule of ammonia, for example, here, this is another ammonia molecule. This is another ammonia molecule here. So you expect to see hydrogen bonding occurring. So if this is ammonia, the lone pair, there'll be an hydrogen bonding between this. So because this is an electronegative, so if there's another ammonia here, so you can see here that it's not just having hydrogen alone. The hydrogen the molecule must have an electronegative element that has a lone pair of electrons. Just like look at water, ammonia also can form hydrogen bonding. So this does have hydrogen bonds. So nitrogen is very electronegative and it has 1 lone pair of electrons in ammonia. So this is another example which you've seen before, water. So you've seen now that water has 2 lone pairs of electrons on it, 1, 2, so it can form hydrogen bond. So now this is a quick summary of the hydrogen bonds. You see that hydrogen, the first example here is ammonia, NH3. You have a lone pair of electron on nitrogen and you have hydrogen atom. So there will be hydrogen bond in ammonia. Then you see water, 2 lone pairs of electron. So there will be hydrogen bond. Hydrogen fluoride has 3 lone pairs of electron. So there will be hydrogen bonding. Do the example we have it in water. So there will be hydrogen bond between this lone pair. There's hydrogen bond between hydrogen and this lone pair. This lone pair and another hydrogen, there will be hydrogen bond. This lone pair and another hydrogen. So the electronegative elements, they must have at least 1 active lone pair, because the site of that interaction is via the lone pairs of electron. So this now, for example, each ammonia molecule can form 1 hydrogen bond via the lone pair on nitrogen. Oxygen can form 2 via the lone pair on oxygen. Hydrogen fluoride can form 3 via the lone pair on fluorine. So let's look at the peculiarity of water, because water, we have, I'm sure you've done what we call the anomalous behavior of water. So the polarity of water causes it to be either cohesive or adhesive. What do we mean by cohesion? Cohesion is the force of attraction that makes a molecule to stick together, and this can be as a result of the hydrogen bonding. Yes, please, Adebayo David, tell your group mates to join this link if yours is not holding. You are free to join any of the groups. So please, you can tell them they can join this group if their own group is not holding momentarily. This is one of the beauties of virtual learning. So even if your class physically, you can join other classes if you're for one reason or the other. And the reason why this is happening is that many of you are not coming to class. We're expected to see about 300 students in each group, and we are having barely 44. So if the class is free, if there are spaces to join, why not? So please call them and tell them to join. So water chemistry, when we look at water, the polarity of water causes it, like I said before, either to be cohesive or adhesive. Water molecules will stick to each other because of this hydrogen bonding. There is this relationship, a strong interaction between them as a result of the hydrogen bonding. That is what makes water molecules stick to one another. Somebody writing here that many people are not aware about the classes. The links to these classes are posted on your LMS. Your learning management system, this is where you interact with your lecturers virtually. And since 2 weeks ago, these links have been posted there. And the links are permanent links. They are not links that change every time. So once it's the time of the lecture, you click on the link, you enter the class. So I don't think anybody will have to be telling you every day that a new link will be posted. So once you go on your LMS, you see the link posted on the LMS, and you join the class every day, because this link will be on throughout the semester. So it is not proper for you to say that you are not aware of the class. You should be, because the information is right there on the LMS platform. So water molecules stick to each other by forces of cohesion. And also, they stick to other polar molecules by hydrogen bonding, and that is adhesion. And that's why we say most times that water is a universal solvent, because it can interact with other polar molecules via the hydrogen bonding. So what are these peculiar properties of water that make water too special? Water has a high specific heat, and this is also as a result of the hydrogen bond. A large amount of energy is required to change the temperature of water. So it has a high specific heat capacity. It also has a high heat of vaporization, and that's the vaporization of water from a surface causes the cooling of that surface. So it has a high heat of vaporization. Solid water is less dense than liquid water. And that is why when you have your ice is solid water. If you drop your ice in a glass of water, it floats. And that also is another reason why when water freezes, water will freeze from top to the bottom. In temperate countries where you have winter snow falling, when water freezes, it freezes from the top, and the underneath the water might still be liquid while the top is frozen, because solid water is less dense, is lighter than liquid water. And that is why aquatic life can be preserved. Can you imagine if water freezes from bottom top to the top? All the aquatic organisms during winter will all freeze to death. So what happens is that the top layer may be frozen with and will be on top, then the liquid water will be at the bottom, and the aquatic organisms can live underneath. And water is a very good solvent because it dissolves polar molecules. It also dissolves some ionic compounds like a salt. It can be dissolved in water. So water is a good solvent, and at times it's referred to as a universal solvent. And water organizes non-polar molecules into either hydrophilic or hydrophobic. So hydrophilic are the water-loving compounds or molecules, while the hydrophobic ones are the ones that do not love water. They have fear of water, so they will not dissolve in water. So we classify molecules, non-polar molecules, as either hydrophilic or hydrophobic molecules. And also the water will cause those hydrophobic molecules to aggregate and assume specific shapes. Water also form ions, as you know, the hydroxyl and the hydrogen ion. So most properties of water that water display is as a result of the attraction that the different molecules have for each other. Water is cohesive, and that means that the molecules of water get attracted to each other. And this high cohesive nature of water is the reason why water has high surface tension. You can see insects can land on water. Even some birds can land on water because of the cohesive nature of water. Some items can float on water because of the high surface tension as a result of the cohesive nature of water. Remember, we said that cohesive nature is what makes the water molecules to stick to each other. That's the cohesive forces. And that is why naturally some water will have high surface tension, and you can have insects or birds or some objects can stay afloat on top of water. Also, water has high boiling points. I've already explained that, relative to other molecules of its size and bonding, because of the large network of hydrogen bonds found in water. So each of a network of H2O, 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 all linked together by hydrogen bond. And it will take a lot of energy to rip them apart, to separate them into the gaseous phase. And that is why water would always have a high boiling point, because you need energy to break this water, the hydrogen bonds in the network of the water molecules. Then in complex molecules like your DNA, we have hydrogen bonds also present. You can have, you see your proteins and the amino acids, they are linked together by hydrogen bond. So these are your different, so the strands of your DNA, the double helix, are linked together. So these different, your adenine, guanine, thymine, cysteine, all the proteins are linked together by hydrogen bonding. So hydrogen bonding all the strands of DNA together, like you said, in the double helix. Also, it holds polypeptides together. It helps enzymes to bind to substrates. It helps antibodies to bind to their antigen. Like when you get your, maybe you get a vaccine now, for example, for COVID-19 is a DNA vaccine. The antibodies will bind to the antigen in the body via hydrogen bonding. It helps in the transcription factors bind to each other in the DNA. Those of you in the medical sciences will learn more of this, or the biological sciences, more of this when you talk about the deoxynucleic acid, the DNA. So now we have a short quiz. Which of the following molecules can have hydrogen bonding? So I want you to type in the chat box the molecules that you expect to have hydrogen bonding. Which molecules here will you expect to have hydrogen bonding? You can put in the chat box. Okay. C and E, water and ammonia. Thank you very much. Even though fluorine is a highly electronegative, two fluorine. So what type of bonding will you see in this fluorine molecule? FF, the diatomic molecule of fluorine. What would you see in fluorine? Fluorine molecule. What type of bonding? Yes, it's covalent. Yeah, that is the intra. What about the intermolecular force that you see in fluorine? In fluorine molecule. In fluorine, what type of intramolecular force do you see in fluorine? Dipole. Yes, that's good. Thank you very much. So fluorine molecule have dipole because, as expected or as illustrated before, the two fluorine atoms are negatively charged. So this fluorine is negatively charged, and this other fluorine also is negatively charged. So it is not it is non-polar. There's no polarity here, but there will be some instantaneous dipole that will be formed between the two of them when they come together. So fluorine molecule will have dipole interaction. Your methane will have what? What type of bond do you see in methane? Methane will form a covalent bond. Your water will be covalent. Your chloromethane also will be covalent, and also you have ammonia would have covalent bond in addition to hydrogen bonding. So answering this question, only water and ammonia would have hydrogen bond because of the hydrogen atom present. You can see, even though there is hydrogen, methane, and chloromethane, the other molecule there is not electronegative. Chlorine here is electronegative, but is not as electronegative as oxygen, nitrogen, or fluorine. So in summary, the different types of electromolecular forces, intermolecular forces, and their strength is illustrated in the table, as you can see. You can see here now that the van der Waals force is a type of intermolecular force. It's weak, and all molecules exhibit this. There will just be a dipole between the negative end and the positive end of atoms in the molecule. Then the dipole, it has a moderate strength, and it occurs in molecules that have a net dipole, like your acetone, ethanol, carboxylic acid, and the likes. Then you have the hydrogen bonding, which is very strong, which can occur between your molecules that have an hydrogen-oxygen bond, hydrogen-nitrogen bond, or hydrogen-fluorine bond, and is very strong. Then you have the ion-ion intermolecular force that occurs in ionic compounds, and this is also very strong, but it only occurs in ionic compounds, while your dipole and your hydrogen bond occurs in covalently bonded compounds. So in terms of boiling point and the physical properties and how bonding affects boiling points, we know that the boiling point of a compound is when the temperature at which that compound gets converted to gas from a liquid phase to gaseous phase. So when you are boiling, energy is needed to overcome this attractive force in the more ordered liquid state. So the stronger the intermolecular forces, the higher the boiling point. The stronger the intermolecular forces, the higher the boiling point. So if that is why water would have a very high boiling point. So for compounds that have approximately the same molecular weight, the one with the hydrogen bond would have the highest boiling point. And also for ionic compounds are held together by very strong interactions, and so they have very high melting points. So with covalent compounds, the melting point depends upon their functional group that is present. So for compounds of approximately the same molecular weight, the ionic strength, the melting point will increase as the type of intermolecular force of attraction also increases. Then let's look at solubility. The extent to which a compound or a solute dissolves in a solvent is solubility. And compounds that dissolve in solvents that have similar kinds of compounds will dissolve in solvents that have similar kinds of intermolecular forces. Like always dissolve like. Polar compounds will dissolve in polar solvents. Non-polar compounds will dissolve in non-polar or weakly polar solvents. So organic solvents like water, which is very polar and has hydrogen bond, has the capability of dissolving so many compounds. Many organic compounds, many organic solvents are either non-polar or weakly polar. Example of non-polar solvents are carbon tetrachloride or hexane. And some of the others are weakly polar, like your diethyl ether. But we know that one of the properties of ionic compound is that they are soluble in polar solvents. So most organic compounds, most ionic compounds are soluble in polar solvents, but insoluble in non-polar solvents. That's why water, HCl is soluble in water, because water is, HCl is an ionic compound and water is polar. So it will be soluble in water, but in most organic compounds, which are non-polar, ionic compounds are not soluble. So NaCl, for example, will not be soluble in hexane because hexane is non-polar, but NaCl will be soluble in water because water is polar. Then ionic metallic bond, this is the bond that exists between metal atoms. And metallic bond is different from an alloy. An alloy is defined as a blend of two or more metal atoms that are blended together form alloy. Just like you have your copper, your brass, you have bronze, you have silver. Those maybe your stainless steel. Your steel is an alloy of silver. You have bronze, you have brass. All these are alloys, but the bond that occur between metal atoms is called the metallic bond. And this is what we see. So the cations in your metals, they are packed in a sea of electrons. And these electrons are not localized on a particular atom, but they are constantly moving around each other. You can see the atoms are unlike the other atoms whereby the electrons are fixed on them. These are not in fixed positions. They are called sea of electrons. So the metal contain closely packed cations floating in a sea of electrons. And metal atoms naturally give up their valence electrons to form positive ions. And these positive ions move freely around they release the electrons, would always move freely around the positively charged metal ions. And all the atoms are able to share these electrons. So you can see that the electrons are not particularly tied to an atom. They can share the electrons together because they are not located per se on one particular atom. They move all about. So the electrons are not bound to individual atoms. So what are the properties of the metallic bonds? They are good conductors of electricity as a result of the electrons that are freely moving about. Metals are malleable and ductile. That is, they can be drawn into shapes, they can be beaten into shapes, and they can be drawn into wires. That's why you see your electric cable contain thin copper metal, which is drawn, which is put into the in the cable. Insulated cable contains your metals drawn into wires. And because of this mobility of electrons that can move freely about, they can conduct electrons. Joy, can you type your question? Joy that is raising hand. If you have a question, you type your question in the chat box. So because of this, they can conduct electrons. And they are also lustrous. That means they can absorb and emit light in regular pattern. So they can absorb and emit light in regular pattern due to free electrons. Then electrons, because they move about, they act as lubricants because the cations can move over each other, they rub on each other, so they can be, the electrons act as a lubricant, which allow the cations to move over each other. But metallic bond is different from alloys because the metallic bond is the bond that occurs in the particular metal, while the alloys are a mixture of two or more metallic elements, or at least one of them being a metallic element or another may not be. And alloys are made by mixing or melting and mixing metals together. And sometimes they contain non-metals like carbon, and their properties are superior to their individual components. For example, stainless steel contains iron, chromium, copper, carbon, and nickel. Naturally, iron is rust, but when iron is alloyed with chromium and nickel and carbon, the quality of iron improves, and that is what gives rise to stainless steel. You can pour water on your stainless steel and it will not get rusty because of the improvements in the quality as a result of the alloy of other elements present. Cast iron in your iron and carbon. Sterling silver that is used for jewelry is a mixture of silver and copper. But what makes it better, silver is very light, but with the copper present, it makes it harder and stronger. So that's sterling silver. Then we have bronze, which is a mixture of copper and tin in ratio 7:1. So this brings us to the end of the class, and see you on Monday. If you have a question to ask, you can type it or unmute yourself and ask a question.